Hello everybody. Welcome to today's session on Know About Research in ISHRAE. I can see, I can see Dr. Dodamani is there, Dr. 𝗬𝗓𝗔𝗘. So welcome. Thank you so much for joining. And this initiative is started so that everyone in ISHRAE can know about what happens at research at ISHRAE. ISHRAE has been funding some projects. The last 4 were at IIT Roorkee, where we have Dr. Das joining us today. And we had 3 more projects at NIT Surathkal, where Dr. Dodamani was there, but now he's moved to IIT Mandi. Then we had IIT Kharagpur, and then we have 𝗬𝗏𝗃𝗃 College in Madurai. These were the last 4 projects. Currently, we have a project ongoing at IIT Madras, and many projects are in the pipeline, but still we have not got the project proposal in hand. Some are there. IIT Indore has given some project which we are reviewing at the moment. So this initiative is to tell all ISHRAE members about what happens in research at ISHRAE, and I welcome Dr. Arup Kumar Das from IIT Roorkee, who will give a presentation of what happened during that project. Of course, some of the time went away in COVID, correct? Yeah, so over to you, Dr. Das. You can share your screen and start the
Thank you, Dr. Roshni, for this nice introduction. Let me start sharing. Kindly let me know if it is visible at your end.
Yes.
Good evening to all of you. It's a pleasure to present the topic once again in front of this gathering. So I have seen that some of the names which are very familiar to me in the attendee list. So thanks for taking out your time to listen this talk. So this project is related to experimental modeling and validation of fouling in air-cooled condenser. This has been funded by Foundation of ISHRAE. Professor Arup Kumar Das from Department of Mechanical Industrial Engineering, IIT Roorkee, mainly was the principal investigator for this one. And along with me, Professor Ravi Kumar from the same department has also helped me time to time during the research. I understand that most of you are actually knowing the terminologies related to fouling of air conditioners, but still, for the sake of completeness, let me spend 2-3 minutes for this slide so that we can understand that what is fouling and how it affects different thermal performances of air conditioning. So, if we see, fouling mainly is a type of pollution which occurs in both laboratory and condenser side. So mainly we were interested in condenser, and that can cause variety of thermal issues. So time to time we have to clean it. So in the left hand side you can see one fouled condenser which is requiring cleaning. Now to see that what happens whenever there are different types of processes in the fouling. You can see the schematic over here. So where you can see there are particles, solid particles, which are getting deposited at a rate of, let's say, 5D, which is the deposition rate. And this is the heat transfer surface on which it is getting deposited. And then on top of that, there is a flow of stream. It can be airflow. It can be water flow also sometimes. It is water-cooled condenser. Mainly we have handled air-cooled condenser. So this is the airflow over here. And due to this flow of stream, you can find out some of the deposited layer once again can be removed from the surface. Let's say the removal rate is 5R. So the deposition rate is 5D and removal rate is 5R. So at steady state, you'll be finding out that the fouling layer having a particular thickness only. Means the deposition rate, whatever we are having from the incoming particles, so those will be equal for the removal rate of the outgoing particles. So fouling friction factor, you can say fouling factor RA. This is nothing but this deposition rate minus the removal rate. And this causes many issues. Means obviously you can understand that some flow of stream is there on top of the heat transfer surface, and there is fouling, air side fouling. So you can have reduced airflow. It will be affecting the condenser capacity, obviously, because heat transfer will be affected, and you can understand that the capacity of the condenser, the entire plant efficiently is getting reduced, and the efficiency of the plant will be also day by day reducing over time. Thermal efficiency, overall thermal efficiency, which will be definitely affected by the fouling. And as there is some particulate matter deposited on the surface, and if the surface is having cascading nature, means many tubes in parallel to each other, so you'll be finding out that the pumping power also increases with respect to time. So there are many, but these are main adverse effects if we are having the fouling associated with that heat transfer surface. So I'll give you a little bit idea about what is the present international research status related to fouling. So this research is very important, which I have found out is talking about the effect of fouling in the air side, and it is actually evaluating the pressure drop in the platinum micro channel coils. Experimentally, they have evaluated this, but they have concluded very surprisingly no appreciable effect on the heat exchanger pressure drop. So this is little bit counter-intuitive, though previous to that in 2009, 𝗬𝗎 et al., they have also said that pressure drop is actually increasing whenever there is fouling. So they have done this experimental work at the bottom figure, you can see, for the fin tube heat exchanger, and they have shown that the biofouling actually decreased the air side heat transfer coefficient, as well as it has increased the pressure drop. So these two are the contradicting views the research community is seeing for this air side fouling. There are some studies, so whenever we have done this critical review, we found out that the dust sizes of these two research efforts were not similar. The distribution of dust size is quite important before taking to the conclusion. There are some other studies also which shows that how much this fouling is important. For example, this study related to Brocker and Braun, so long back in 1998. So this has been done on rooftop air conditioners, and they have showed several types of faults. And you can see the fourth one in this row, and you can find out that condenser fouling was also part of the study. And in the right-hand side figure, you can see that condenser fouling is actually taking a very lead role, and the fault intensity may reach in the peak season somewhere around 30%. So, and this is even in some case, it is higher compared to the refrigerant leakage loss also. So obviously the condenser fouling is not to be ignored, and some numerical analysis has been also done, because in my presentation today, I'll be giving some numerical perspective also. So I thought to touch the literature review related to the numerical side. So you can see over here that in 2009, 𝗙𝗪𝗧 et al., so they have showed that how the refrigerant leakage, standalone refrigerant leakage can cause faults in the air conditioning plants. But surprisingly, there is no experimental study on fouling faults till date. Standalone experimental study is not there reporting the fouling. To see these kind of lacuna of literature overcome, so the foundation of ISHRAE and Professor Ravikumar and myself, we have jointly framed the proposal, and the proposal has been accepted by foundation of ISHRAE for funding. And these were more or less the activities or tasks in the proposal. So, the project started on 25th September 2020. You can understand this is in the COVID period only. Second phase of the COVID was there in that time. So So the activity one was obviously the procurement of the experimental facility and the fabrication to set up. By the way, we have taken 1 ton capacity condenser, copper condenser, which is having 5 fins per centimeter. So this was the specification given by Foundation of ISHRAE at that time. And in the activity 2, first with one set of experimental setup, we are supposed to see that how fouling varies and if there is any fine-tuning needed in the experimental setup, so that we are supposed to do and report the fouling data for at least one set of experimental part. And then after getting confidence in the activity 2, so in activity 3, we have actually parallelized the effort, and we have made 4 different types of experimental setup side by side, where we can test for 4 different types of contaminated air. And mainly we have varied the particle diameter. For example, 10 micron to 30 micron we have taken. And for different weather conditions. So the weather conditions which has been given to us is of this fashion. So first one was dry bulb temperature 40 and wet bulb temperature 30. Next one is dry bulb temperature 35 and wet bulb temperature 30. The third one is dry bulb temperature 33 and wet bulb temperature 24. And the last one is dry bulb temperature 30 and wet bulb temperature 20. So you can understand that 4 different types of particles we have handled, so different sizes and 4 different conditions. So overall 16 experimental runs we have done for it is a prolonged experimental run. Soon I'll be telling you the time frame for which each experiment runs, because it has to be completely fouled so that the steady state, which I have told you earlier, can be achieved. And then in activity 4, what you can do is that you can let me see if I can move it up. So in activity 4, what you can do, we have tried to do some sort of data fitting so that we can give a model so that it is applicable for other conditions apart from the tested one. And activity 5, last one, which has been added later on, but still we have delivered that one, that we, after the model development, obviously we have to test with some data which is not falling in the range of the experimental readings and some other parameters away from the experimental regime, and we have found out good match is there. So this project has been completed within 30 months of time from September 22. Coming to little bit detail about the experimental setup. So you can see in the top figure, so it is a pictorial view of the setup. You can see to maintain the conditions, that means the temperatures, dry bulb and wet bulb temperatures. We have connected the setup with a climate simulator. So at IIT Roorkee, we are having a climate simulation lab, which is a walk-in chamber basically. It's a 5 meter by 5 meter chamber where we can maintain temperature from 45 degrees centigrade to minus 20 degrees centigrade. And the relative humidity can be also varied from 75 to 80% to a little bit of dry conditions also up to 20 to 30%. So what we have done, this climate chamber is having one anti-chamber also. So the anti-chamber is maintained in the normal conditions. That means somewhere the temperature can be varied from 15 degree to 45 degree with a very high accuracy of 1 degree centigrade. It can be maintained for prolonged hours. And the humidity range we have set in the antechamber in the range of 40% to 75% for the entire range of 30 to 45 degree, which was our target level of the weather conditions I have shown in the previous slide. Now the bottom one, before going to the bottom one, first I'll be showing in the right one, which is the actual experimental facility you can see. So in the experimental facility, what we have done, you can see the air condenser over there, which is facing the air. And there is one dust hopper. On top of the dust hopper, we can give a particular type of dust. Soon I'll be showing you that what are the different dust types and sizes we have taken. So from that dust hopper, the dust comes out through one port over here, which is valve controlled. There is a fan which will be taking out the atmospheric air or the controlled air. So controlled air from the antechamber of the climate chamber. So that air will be flowing over this condenser, and on the path of the airflow, this dust hopper will be releasing the dust. So the air will be carrying the dust and causing expedited fouling on the condenser. So the condenser is connected with the evaporator and the compressor and other parts of the refrigeration circuit. And at the bottom of the air duct, you can see there is one conveyor belt which collects all the dust particles which are not getting carried away by the air, and it is actually putting it on a collection hopper. And time to time, what we do is we feed from the collection hopper back to the dust hopper, and obviously some makeup particles are supposed to be also given, as because at the outlet the air is always dusty even after the deposition around the condenser. So this is the more or less the schematic diagram of the single experimental setup. Now in the bottom left side, you can see the aerial view where you can see the antechamber at the background, which is having a grill cage. You can see, so inside that we are having the antechamber, and then from the antechamber you can see one pipe is coming, PVC pipe is coming, which is carrying the air, and then that air is actually getting mixed up with the ambient air, and then it is being flown in the duct. So the duct can be seen, the front setup duct at least you can see. The same thing is in parallel fashion in the backside 4 setups. And on the top of the duct, you can see the hopper, which at the bottom with a different gating system and then different valves, the release of particle at a particular rate can be done. And at the back side of the of this duct, you can see the evaporator and other setups which are required for running the air conditioning facility. So this is the parallelized setup which we have developed at the end, and these experiments are running at least for 1.5 months continuously, day and night, and so that we can have expedited fouling and have a steady state situation even after the removal of particles with the air. In the right-hand side bottom, you can see some of the pictorial view of the expedited fouling of the condenser with different types of particles. So you can see at the right-hand side, we are having fouled condenser with 20 micron size dust. And at the bottom one, the right-hand bottommost one, you can find out that is a fouled condenser of 30 micron size dust. And a close-up view near the tube, if you can see, the tube is also getting fouled. At the bottom of this pictorial view, you can find out the tube frontal face at least getting fouled. Later on, whenever the fins were clogged, it was very difficult for us to see even the tube. So those pictorial views are not there, but we estimate, and we have also seen from the numerical simulation that the entire tube gets fouled even at the backside. Okay, so these are pictorial views which we have presented for different experimental readings. Now, if I just give you the parametric variation of our experimental setups. So these are the data or the experimental readings which we have to take. You can see the set dry bulb temperature and wet bulb temperature. For that, the respective relative humidity I have shown in the 4th column. So 40%, 70%, and 50% respectively. With that, a different dust size variation, 10 micron, 15 micron, 20, and 30 micron. So altogether 16 expedited fouling experiments we have done in parallel during these days. And a little bit giving you the idea about the particles, what we have fit in the hopper. So we have collected the Ganga Bank dust, and then we have done milling of that Ganga Bank dust to get 10 micron dust particles. So that was also one huge effort, because you can understand for continuous experiment for 1.5 months, you require a very good amount of dust quantity. So we have collected that. We have gone through different milling process so that we have this 10 micron size. On the right hand side, you can see the ACM image of that one also. To have little higher size, we have taken countryside clay dust, which is reddish in color. And to give you the understanding of different industrial particulates also, we have taken industrial soot, fine grade and coarse grade. these are also once again passed through different milling process so that we get more or less uniform particle sizes. So same images are showing more or less uniform particle sizes, which are having average diameter of respective 15, 20, and 30 microns before feeding. Now these dust particles, once we obtain, then we have actually dried up, because once it is having moisture in it, it will be coagulating, and the particles will be having larger sizes over time. Even in the hopper also it can coagulate and it can change the size. So these are air dried, so that the particles are having no moisture in this, and we are having free flow of dust in the air duct after this getting system. So now here I'm showing you some of our results for this fouling mass. By the way, let me take you to the experimental setup to explain. So you can see this condenser is over here. The condenser is actually placed on top of a tray, and the tray is placed on top of one sensitive balance system, weight balance system, which measures the mass collected by the condenser tubes around it, and the difference of mass over time we are considering that is the steady fouling or deposition rate on the condenser tube. So whenever we do this kind of weight measuring, so by the way, this has been done for every day at the morning, so for all 4 setups. So whenever we do that, we have to disconnect it from the rest refrigeration setup. So we disconnect that, we weight that, what amount of dust has been deposited for the entire day, and then once again we connect it back for the next day's. So like that, the data has been collected. Now the data, whatever we have got, is being shown here pictorially. So in all the plots, you can see that somewhere, that though the time is varying for different types of weather condition and the temperature, but that there is some steady state achieved, which is nothing but, as I have showed you previously, the amount of dust deposited and due to the air flow, whatever amount of removal is there. So that is balancing each other, and the constant fouling rate can be seen over there. And in this kind of studies, you can see that obviously the effect of particle is there. You can see that the 30 micron particle is actually having higher deposition mass, which is at the bottom 4 graphs, and lower particles are having the smaller fouling mass around the tubes and the condensers, fins. And obviously the weather condition is also having effect. You can find out that whenever the temperature is higher, so obviously the fouling rate is actually lesser, and whenever the temperature is lower and the humidity is getting maintained somewhere near 40% or 50%, the fouling rate increases. So with this data of this steady state fouling mass, we do the study. So this is the final experimental run after 1.5 months around experimental data. So this we call as a stable fouling mass. So stable fouling mass in the entire condenser, you can find out in some cases it has gone up to nearly 7 kg also. So the fouling mass has been actually plotted in the scale of these 3 parameters. Obviously, one is the weather condition, dry bulb temperature, relative humidity, and obviously the particle sizes. The right-hand side plot shows the variation. So you can see the 3 axes, dry bulb temperature, relative humidity, and fouling mass has been shown over here for 4 different particle sizes. And from there, we try to develop the correlation. And we found out that in place of going for polynomials, the simple relationship like fouling mass equals to some constant into dry bulb temperature, then another constant into relative humidity, and the 3rd constant into particle size plus 4th constant suits better, and it is having very good matching with the experimental data. And you can see in the right-hand side where we have shown the normalized residual variation with normalized quantile of the developed correlation, and it's having very good match with the developed correlation. So after getting satisfied result with the correlation, we also tried to see that what is the effect on the heat transfer and the pressure drop. You can see in these two graphs, so we have showed that how much heat transfer is actually deteriorated and the pressure drop has been increased. So you can find out that in few cases, like the larger size particles, somewhere around 20% capacity has been dropped. That means you are running the capacity 80% lesser compared to the ideal one, and because this is fouling and the entire surface is actually getting deposited by non-conducting materials like dust. And in the right-hand side bottom, we have shown the pressure drop, and you can see in some cases, depending on the deposition rate, the pressure drop has reached somewhere around 2.5 times of the normal one. So these two are can be correlated with the fouling mass, though that was not the target of our study, so we have not performed the correlation of the heat transfer and the pressure. Well, then towards the end, it has been told to us that the pressure, the correlation, whatever we have developed, can that be validated with some new experimental data, so that the applicability of the developed model can be checked. So for that, we have done once again 4 other experiments. So you can see these are not those which earlier I have shown you with the same particle size though, but the conditions are different. And this graph shows the predictability. So the fouling mass calculated by the correlation shown above, shown previously, and experimentally whatever you obtain, that gives you a very good match within ±4%. So this shows the applicability of the developed correlation, which has been done based on the 16 experiments whatever I showed previously. Okay. Though the numerical effort was not a part of the the project, but side by side we have also done some numerical analysis. So I'll quickly show you some of the results. Though you can understand the numerical simulation cannot go for 1.5 months or so. So this is a very short time simulation, but this also has shown similar kind of insights, whatever I have shown you in the previous experimental effort. So for that, we have taken this kind of geometry. You can see in the top left side figure. So air inlet is there, and then dust particle once again is having at the top wall at a particular location from a distance of the condenser pipes. And we have tested different arrangement of the condenser tube, so inline and staggered. A representative mesh is being shown in the middle section. And for modeling, we use Eulerian-Lagrangian simulation. So continuum phase, which is air, has been dissolved by continuity and momentum equation. And then the discrete phase, which is the particles that has been solved using Newton's second law. And the respective force fields are modeled appropriately so that we can get two-way interconnection between the models. And you can see the different inline and staggered arrangements of the tube has been shown over there. And the respective paths of the particles are shown at the bottom. You can see that the particles initially, the initial first two planes, if you see, those were trying to bypass the tubes, trying to deviate from the top or bottom, and not to deposit on the surface. But whenever it is going to the third and fourth row, you can find out it is actually depositing over there. By the way, that is the location where the tubes are actually fed. Okay, and then in the right hand side, you can see for the staggered arrangement, and left hand side you have the inline arrangement. And inline arrangement, whatever dust particle we have got deposition, that we distribute uniformly over here in all the tubes. So you can see the front tubes only get the higher amount of deposition, but towards the back also you can see due to the decirculations, some of the tubes are also getting deposited volumes. So these are different conditions for which we have tested. In the left hand side you can see, so two different cities conditions we have taken for New Delhi and Kolkata. So these are different particle diameters which we have found out with concentration and their respective densities from the data of weather stations, and this we have fed in the dust hopper as the inlet plane of the top of the geometry. By the way, in the right hand side, I have shown the equations which we have used. So the first three equation is nothing but your Navier-Stokes equation, having a force field F which is coming from the particle, and we use 𝗬𝗓 turbulence model to resolve the smaller scale eddies in the model solution. And for the particles, we have used Newton's second law, where drag force and gravitational deposition has been taken into consideration. By the way, drag force, how we calculate, has been shown over here in the bottommost equation, having the drag coefficient dependent on the Reynolds number of the particle. Reynolds number is being calculated based on the characteristics diameter of the particle, which will be coming from the particle size distribution taken for a particular city. And by integrating this Newton's second law, we can get the velocity, and once again integrating this one, we can get the location at the next time step. So the forces are being calculated and fed to the Navier-Stokes equation, and from the velocity of carrier phase, the particle forces, that means the drag force is being calculated. So you can see in the drag force calculation, we have U minus UP, where U is the carrier phase velocity. So this is a tutorial view of the particles. You can see that after deposition at a particular time, you can see that those are getting deposited around the fin tubes, and you can see that very high particle density is there around the tube, which we have measured, and then we have plotted in the right-hand side figure to show that over time how the tubes are getting fouled. Different tubes we have shown over here. By the way, this picture is for staggered arrangement, so similar inline arrangement also we are having. So you can see the simulation has been only run for 5 seconds, but you can see that a good amount of space has been actually occupied by the fouled tubes. That means the particle depositions. This figure show a little bit of velocity variation over distance whenever we traverse in the downstream side near to the particle, near to the condenser tubes, and you can find out that the velocity is lowering down over there near the condenser tubes, as because it is facing the fouling effect. And in the right hand side figure, you can see that at a different cross-sectional plane, if I try to show you that what is the velocity. So obviously you can understand that between the tubes we'll be having the higher velocities, but near the tube you can see the deposition is actually causing the velocity lower, and it is increasing. The layer thickness is increasing over time. Okay, coming to the velocity vectors in terms of the streamline plots, you can see that near the tube at the exit plane we are having circulation. So this circulation also can cause particles to deposit at the backward side tube rows, so which we have also noticed over here in the simulation I have shown you earlier. And if you see about the pressure drop, a very good amount of pressure drop is increasing within this 5-second time also we have seen. In the right hand side figure, I have shown the particle trajectories. So you can see that before facing the tubes with the fins, you can see that particle is having higher velocity or higher speed at the center plane. But whenever it is interacting with the particles, you can find out in between the tube rows, it is having the higher velocity. But in front of the tube rows, there is a stagnation point, and particles are getting deposited over there. In the back side of the tube, whenever the particles has passed, so you can see that at the bottom side and the top side, we are having higher velocity, which has not faced the tube, which is empty zone on top and at the bottom of the tube. And at the back side, you can see the recirculation is also causing the increase of the velocities. And particles are getting deposited at the right-hand side boundary. So to give you some numbers, so these are the fouling thickness variations for different fin size variation and fin spacing variation, and different tube diameter variations, numerically whatever we have found out. And we have seen that whenever the fins are getting closer to each other, there is a huge rise in the fouling thickness that is expected, but it is not a linear trend what we have obtained, because fouling from one tube is actually interacting with the fouling from other tube, and it is getting enhanced, not in a linear fashion. Fouling thickness is also having role on, the diameter of the tube is also having role on fouling thickness. It is well understood. And you can find out that the highest fouling we have obtained in the case of some cylinder diameter, which is in the intermediate zone. In the right-hand side figure, you can see the pressure drop for the clean condition and the fouled condition. By the way, pressure drop contour I have shown you in the previous slide. So we calculate the fouling thickness based on this formula shown on the top, which is the volume of particles deposited divided by the area of the surface into number of the particles. So like that, the fouling thickness has been calculated and pictorially has been shown. And pressure drop, I have just now explained that this is increasing the pressure drop, and you can see in some cases towards the end for high velocity, it is almost 25 to 50% increase in the pressure. So these are different deposition fraction. By the way, deposition fraction is a number which we have proposed over here, which is nothing but at the bottom it is written mass of the dust particle deposited on the heat exchanger divided by the total mass of the dust injected into the air system. So how much it has been actually staying on the condenser tube. So that is the deposition fraction. So deposition fraction for two different cities condition we have shown over here, and for different velocities. You can see that both the velocities as well as the weather conditions and the particulate distributions are having a great role to play in this. By the way, in the right-hand side figure, we have shown that what is the rate of reduction of the heat transfer coefficient, and you can find out within even 3 seconds of simulation, we have found out a short of nearly saturated simulation. So down the line, if you do for longer run, so obviously it will be getting a saturated trend. Well, with this, I'd like to stop my presentation, and I'll be happy to interact with you. Please let me know if I need to stop sharing.
Yeah, thank you, Dr. Das. I think it was quite a challenging conditions under which you were working. I have got two questions as to how did you choose those 4 temperature and relative humidity conditions?
Yeah, those have been given by the foundation of ISHRAE members at that time. So this has not been chosen by me. It has been told that these are the conditions which are majorly used in different industries. So that's why these conditions have been given to us. So this has not been chosen by us. It has been told us to do.
Okay, there is one question in the question and answer box which says, what's the minimum tonnage of system falls under this maintenance schedule? I don't know whether you can understand what that means.
See, this experiment has been done for 1 year only. I understand that obviously tonnage may, because the size is increasing, so may have some effect, so which requires some more investigation. I am not sure at present that how the tonnage is giving effect on the fouling. At present, I am not sure because experiments have not been carried forward.
Okay, and all the condensers, the tubes are staggered, right?
Yeah, so in the experiment, tubes are staggered.
Yeah, and also the fin spacing is a standard which is available
in the market. Yes.
In market. Yeah, thank you. Anyone is having, okay, one more question. In which software the simulation was performed? I thought COMSOL.
Yeah, simulation has been performed in COMSOL. So this is having the both Euler and Lagrangian framework. So we have used that.
Okay, if anyone is having questions, you can either write it in the chat box or the question and answer box.
Should I open the chat box?
Yeah, you can.
Okay. Yeah, I can see one more. Yes, fouling is uniform throughout the bundle. No. I'll show you the pictorial view. I do not know here you can see or not. So towards the end, whenever we are having steady state fouling, you'll be finding out that it is completely fouled and it is more or less uniform everywhere. But at the beginning, obviously the tubes which are at the middle, those get fouled, and then the corners will be getting, and then the first row gets fouled first, then the second row, like that, you know. In the numerical simulation also, I have shown you similar.
Okay, and this climate simulator lab is already existing in your...
Yes, at IIT Roorkee. Even before the project has been approved, it was. We do several other work over there using the climate. Yeah, I can see another question. How the fouling is calculating according to the fin gaps and tube sizes? No, we have not varied the fin gaps and the tube sizes. Yeah, numerically we have done, not experimentally. So experimentally we have not varied the fin gaps and tube sizes. So the fouling mass is actually not tested that what is the role of this fin gaps and tube size. But numerically, I can tell you that the gaps of the fins are very important. If the fins are having very less gap, obviously the fouling will be more, but it is not having a linear relationship even. It is having one exponential relationship. That means if the gap is reducing, the fouling is actually increasing exponentially due to the particle-particle interaction between deposited between two fins. And obviously tube sizes also, as because tube sizes are also stopping the particles to flow around, and the recirculations are there around the tube. The vortex which are generated around the tube, those are actually involved with the tube sizes. So those are also giving effect. Numerically, we have seen the tube sizes and fin gaps are also having a great role to play. Yeah, fan distance from the condenser is fixed. So it is fixed. In the experiment, the fan distance from the condenser is fixed. So far I recall, the fan distance was somewhere around 2 feet. 2 feet. The hopper was somewhere around in between 1.5 feet to 2 feet. Numerical simulation, what was the air particle flow? No, Professor Agarwal, that was not uniform. So based on the particle sizes, I have shown you for Kolkata and Delhi. So depending on the particle size distribution, we have actually failed. So that was non-homogeneous particle distribution. And you have also questioned after each experiment, how the fins were cleaned. So we have not cleaned basically. So each experiment has been done with clean condenser, and those condensers we have preserved because before the project ends, so we can show you the pictorial views. So all the pictorial views are with us. We have not cleaned the condensers. Does the tube material have any effect on fouling? Oh, definitely it should be, because the surface is having a great role to play. If the surface is having more hydrophobic nature, so I feel that fouling will be lesser. So copper tube or aluminum tube or any other tube, obviously that will be mattering. But experimentally, we have only used copper tube. I'm not sure how that varies, but I understand there should be some role of the tube material also. Numerically also we have not tested, because our model is not modeling the solid side. So it is only the fluid side modeling. Yeah.
Yeah, I think that's all the questions.
No, one more I can see. What is the effect of fouling on square pitch tube and triangular staggered pitch? Which design is more prone for fouling? Now, numerically, I have seen that staggered one is more prone for fouling, as because the blockage ratio is more, and one vortex is actually being controlled by the another vortex. So those are actually cross vortexes, whatever we have seen. So, but experimentally, we have not varied fin pitches, etc. Yeah, one more I can see. How much CFM the foulings are tested? We do not recall the number, but expedited fouling we have done. I'm not recalling the number, but it was sufficient enough to give the flying moment of the particle. So what we have to do, see, the air velocity is in such a fashion that the particles should not be falling much. If it is falling much, then our the recirculation rate from the collection hopper to the dust hopper is actually more. So we have given the air flow rate in such a fashion, the fans have been chosen in such a fashion that most of the particles are getting carried away and it is actually interacting with the condenser. So, but I'm not recalling at present that what was the foul CFM for the fans. I'm not sure. What about wet fouling? No, dusts were in the experiment. Dusts were completely dry. So wet fouling we have not tested. Because wet fouling, what will happen? The particle sizes will be varying depending on how we were placing on the dust hopper. Even the dust hopper design and size will be also changing the results. And as we are interested in the steady state, I don't think that the result, whatever we have shown, the steady state result, that is going to vary much with respect to the dust sizes and whether it is wet or not. I don't think those are important, but obviously, depending on these parameters, the total runtime to reach the steady state may change.
So one of your findings was that at higher relative humidities, the fouling is more, and also the higher the dry bulb temperature, the fouling is less. Correct?
Yes, that is for the air side.
Yeah.
So you can say that that is giving you some idea about the atmospheric moisture, but that moisture, I don't think it is sufficient for coagulation of the dust particles, which are very fine in size. So that requires a large amount of moisture to get coagulate with each other. But obviously that gives some idea that how the moisture content affects the rate of fouling.
Yeah, some more questions are there.
So next is Dr. Agarwal said, what relation exists between tonnage and amount of fouling? I really do not know because we have got the chance to see only for one tonnage, 1 TR. So I feel that as the tonnage is increasing, so the condenser sizes will be changing, and the construction of the condenser will be also changing. That tonnage is also having some effect, but within the scope of the experimental run, we had nothing to do, test for that one. So the tonnage was fixed actually because the experiments were too time taking. So we have not got the chance to vary the tonnage. Yeah, role of humidity in fouling. Just now I said that obviously humidity is having a major role. If it is more humid, I have shown in the experiment as well as in the numerical simulation, that humid air is actually causing more deposition. And it is reaching to the steady state condition also faster. So fouling mass, steady state fouling mass as well as deposition rate, both are actually higher for more humid air. Yeah, really intense and deep experiments need based research, very crisp and okay. Thank you.
Some appreciation from Dr. Agarwal. Yeah.
Thank you.
One more.
I can see one more question. How the fouling affect the heat transfer coefficient if humidity increases, calculated in the... Yes, this we have calculated. I have shown you one slide also. I'll take you to the slide. Yeah. So in this slide, you can see that the heat transfer, though it is not a coefficient, but I can say the heat transfer I have shown over here. So you can see that whenever the humid air is there, so you are the last 4 readings you can see. So those are actually causing a great deal of great amount of reduction in the heat transfer capability. So obviously the heat transfer coefficient is also reducing. So humidity is having a big role to play in this. We have not given the correlation of the heat transfer coefficient as a function of the humidity ratio and the dry bulb and wet bulb temperature, but the fouling mass we have given. So from the data, one can always find out similar equation or correlation.
Yeah, okay. So thank you, Dr. Das, for sharing all your inputs.